Hi guys, today we're going to be looking at continuity of a function. Or we can think of it as, is it continuous or discontinuous? And we'll start off by looking at a few graphs. We know here we've got a nice linear function and a cubic function. And we don't really know these ones, but this is a trigonometric function here. And when I trace those curves, if we notice there are no breaks in them, or holes, or they don't jump values, these are what we call a smooth, continuous curve, right? We go along, it doesn't have any jagged, sharp edges, or holes, or jumps. Now let's go ahead and compare these three graphs to these three graphs. Here we can see this one kind of looks like absolute value, but then we get to 2 and it makes a jump. Or we could look at this parabola where it comes down and back up. Oh, but there's a hole. Recall that when you have a not filled in circle on a graph, that means that's a point that we do not count. And then last, we have this function here. This is the reciprocal function. And when we trace it out, we've got nice smooth curves, but there's actually a gap right down the middle here where we never cross certain values. These are all called discontinuous functions, and they have different names for these different types of discontinuities. This one here is called a jump. This one here is a hole. And this one here is what we call an asymptote. And an asymptote is actually a line that runs through our picture. And if I were to go ahead and come in here, I could draw. This actually has vertical and horizontal asymptotes, meaning that there's these imaginary lines on the axes that this function can never cross. So the question here is, what was the difference between these, the first group of graphs here and the second group of graphs? And the difference is, the first one, these are all continuous functions. Smooth, continuous curves, they have no holes or jumps or asymptotes. Whereas every single one of these has a part where the continuity of the function is not complete. So here's our definition for continuous. A function is continuous if there are no holes, breaks, or jumps. This graph is what we call unbroken, right? So those first three pictures we looked at were all unbroken, continuous graphs. Discontinuities are X values that create holes, jumps, asymptotes, or breaks in graphs. There are three types, as I showed: holes, which are called removable asymptotes. And let me pull my picture up here of those different types. 1 second. So here we've factored something out of this equation that it gives us this hole. Those are called a removable discontinuity because you factor something out of the equation. A jump is like this, and these are typically represented by what we call a piecewise function. And these are functions that are, they have different different definitions for different parts of the domain. So here, this function could be that f of x is, well, here we have the absolute value of x when x is less than or equal to 2. And then it's the line 3 when x is greater than 2. And that is this piecewise function, and they have these kinds of definitions where you have an interval that shows you where that graph will be put. And then finally we had asymptotes, right? These lines that we can never cross. And it's actually the lines that the function can come infinitely close to, but never touch. So when we look at this picture of these lines, we can see this can get infinitely close to this y-axis, and it can get infinitely close to the x-axis, but it will never ever touch it. That is the definition of an asymptote, getting closer and closer and closer, but never reaching that. Okay, I'm going to skip this example because I don't think it's a little confusing. Okay, we want to identify the discontinuity. Here we have a function that comes along that's one shape, and then we jump. Well, this is a jump, right? You can always tell a jump discontinuity because it actually drops or rises significantly to another value, right? So instead of being at 2 or at 1 up here at 4, it really drops down here to, it looks like -0.5. So that's a jump discontinuity. Here we've got a function that just looks like a line, but it's got this open circle. And we call those, that's a hole. And I mean, if you look, it looks like a little hole, right? Those ones are pretty easy to remember. And this comes from a cancellation. Right, something was canceled. Sorry, my cancellation's a little rough there. Oh, here we've got another picture of this lovely smooth graph, but we come upon a hole. That is a hole discontinuity. Here they've actually drawn in for us that we have this line that the function can get really close to. There's actually two, that line at negative, looks like about -3 on the x-axis, and then we've got so this line x equals 3, but we've also got the line y equals 0, which is the x-axis, and that it looks like it cannot cross those. So when we have a line we can't cross, that is an asymptote. And we call this kinds of, speaking of, like, we've been talking about end behavior, we call this asymptotic behavior. So two main reasons for discontinuity. One is that you get a 0 in the bottom of a fraction. So it turns out that there's a couple different cases here. So we can either cancel out the entire bottom of the fraction and create a hole. Right? This is when we cross out, is when we have a hole. Holes are what crosses out. And vertical asymptotes are what is left in the bottom. Right? So, and we'll see this in an example. And then piecewise functions that do not match. So having something, this is that where we get the jump, right? Let me go back and look at one of our examples here. Right, but here is a piecewise function where now if this graph had started here, we could possibly have that, we would have a continuous function because it would be defined at that point of 2. You wouldn't have this large jump between the two values. So piecewise functions not matching up on their y values is what causes a discontinuity. Okay, let's look at a few examples here. We are going to have to factor this expression x squared minus x minus 2. And if you recall that when we're factoring a quadratic like this, we just want to know what number multiplies to -2 and adds up to -1. I need two numbers that multiply to -2 and add to +1. Well, I'm thinking since I've got x plus 1 on the bottom, it's probably going to be a +1 in there. And indeed, if I multiply that by -2, I get -2 as my product. And if I add -2 to +1, I'm going to get 1 minus 2 is -1. So that will be our two factors, 1 and -2. So let's go ahead and rewrite the top of my expression, x plus 1 multiplied by x minus 2, right? That's my factored form from my factors I found here. And it goes over x plus 1, right? Now, I can cancel out these two factors, right? They're identical, this x plus 1 and x plus 1. So I'm going to cancel those out, and now my entire function just becomes this line, f of x equals x minus 2. But I've had a cancellation. This creates a hole. And if we want to find out what that hole is, to find the hole, set the denominator equal to 0 and solve for x. This will give you the value for x that causes the discontinuity. So here I had x plus 1 is what I canceled out. So I'm going to set that equal to 0. When I subtract 1 from both sides, I end up that x equals negative 1. That is my discontinuity. Right? I have a hole at x equals negative 1. Now, we'll see that on this next example, well, we know how to refactor this, right? We just did that on the previous one. So I can rewrite this as x plus 1 over x minus 2. And now I have these two canceling out, and I'm going to be left with an expression on the bottom of my rational function. Recall, though, that I still will have a 1 on the top of this function. So this simplifies to 1 over x minus 2. Now I've been left with something in the bottom. So here I canceled out the entire bottom, and it gave me a hole. I'm left with this, so I know I'm going to have an asymptote. This having an expression still on the bottom of my fraction is the reason I know it will be an asymptote. Here the bottom canceled, it created a hole. Here the bottom does not cancel, so I get an asymptote. And it's the same as before. To find the vertical asymptote, we will again set the denominator equal to 0 and solve for x. In this case, I was left with x minus 2. I'm going to set that equal to 0. We can add 2 to both sides, and we get x is equal to 2. So I have an asymptote at x equals 2. So again, cancellation created a hole. When I could not cancel the denominator or the bottom of this rational function, then I was given an asymptote. And recall that when it says x equals 2, that's telling me the vertical line x equals 2 is that asymptotic line. Here I'm looking at this problem, and I'm thinking, well, I can't factor an x out of the bottom of that. I believe this is really as simplified as I can get it. So I have a fraction, and the bottom of my fraction will not go away, so this is an asymptote. And to find where it's at, we'll take 2x plus 4 and set that equal to 0. Start by subtracting 4 from both sides, and I'm left with 2x equals negative 4. Divide off that negative 2, and my final answer is x equals negative 2. So we have an asymptote at x equals negative 2. Right? This was not factorable. So if you cannot factor a rational expression, then you'll just need to go ahead and take the bottom and set it equal to 0, and that will find you the asymptote. Okay, we've got a factoring one here. We've got x squared minus x minus 12. So a number that multiplies to negative 12 and adds to negative 1. For the sake of time, I know that those numbers are going to be negative 4 and positive 3. Because negative 4 times positive 3 does multiply to negative 12, and negative 4 plus 3 equals negative 1. So let's go ahead and rewrite the top of my expression. X minus 4 times x plus 3. Oh, and look, we've got matching factors now. Again, recall that if I'm going to cancel out this factor of x plus 3, then the bottom of this has just canceled out, and I'm going to get a whole, because the bottom is gone. Right here, I had to solve for the bottom. There was something still left in the denominator. Here, the denominator went away. That means it's a removable discontinuity, which is a whole. And to find where that whole is, I'll take x plus 3 and set it equal to 0. Go ahead and subtract that 3 from both sides, and we get x equals negative 3. The whole is at x equals negative 3. Here we have our piecewise function, and it's asking us to identify the discontinuity. And here we can see this is the jump. There's not a whole lot of calculation we need to do with these types of problems. Mostly is to recognize that we have a jump at x equals 2, and that would be our solution on that. Here another example of a jump discontinuity, right? We jump from up here down to this value, so we have a jump at x equals 1, right? That's where the function becomes discontinuous. And I'm going to go ahead, we don't have a graph for that last problem. So I will go ahead and stop now, and if you have any questions, please ask.